So, welcome everyone, and this is lecture number 8. I think this is lecture number 9, not 8. Should be lecture number 9, not 8. And in this lecture, we are dealing with MEC, one of the other scoring topics. MEC, EMI, AC, electric current, electrostatic, capacitance. These are the topics from where you can expect 4 to 5 or maybe more questions in a JEE advanced. So I hope you have an idea about this topic. Yes or no?
Yes, sir.
This topic also includes some part of magnetism, bar magnets, and all. We'll just quickly go through them first of all, and let us see how do we go about it. Are you okay with this topic? Have you gone through this topic before?
Sir?
Have you studied this topic before?
Yes, sir.
Okay. So let me just go through this in very short. And where is my this? Okay, go through this very short. And remember, what we are doing here is also valid for one more case, where this case is the case of electric dipole. Do you remember electric dipole? Do you remember electric dipole?
Yes, sir.
Electric dipole and magnetic dipole, you will have similar formula coming. This is the field due to a single magnetic pole. Do you know this? V naught by 4 pi into m by r square. This is same as electric field due to a point charge, k q by r square, where k is 1 by 4 pi epsilon naught. Wherever epsilon naught comes in the denominator, mu naught will come in the numerator. We all know this, yes or no?
Yes, sir.
Every magnet has two poles, north pole and south pole, and therefore every magnet has something known as the dipole moment. Do you know this dipole moment?
Yes, sir.
Do you know how do you calculate the dipole moment of a magnet? Do you know how to calculate the dipole moment of a magnet? How
Sir.
do you calculate the dipole moment of an electric dipole? Whatever we are doing for magnetic dipole is same as electric dipole. What is the dipole moment of an electric dipole? Charge, positive charge multiplied by the dipole axis. Do you know this?
Yes, sir.
Q into 2L. And remember the dipole moment, how it is directed from the negative charge to the positive charge. That is known as the dipole axis. Do you know this?
Yes, sir.
Similarly, we have dipole moment of a magnet, and therefore we will have dipole moment for anything that creates a magnetic field. A current carrying loop creates a magnetic field, and therefore you will have magnetic dipole moment of that loop as well. Are you getting my point, bacha?
Sir.
Okay. Now, whatever questions we are doing, it may be looking like questions on magnet, but this can very well be, if you forget the magnetic north and south, they become question on electric dipoles. Do we understand this?
Yes, sir.
And I hope that you know the basic formula. So what I'm going to do is straight away give you a question, and I'm sure that you can do this question. Don't think it off as a question on magnetic dipole. Take it as question on electric dipole. Question on electric dipole has not come for a long time. Maybe this year. Find a magnetic force on a short magnet. Instead of taking it as a short magnet, you can take it as a short dipole of magnetic dipole M2 due to a short magnet of magnetic dipole M1. The distance between the centers is normally given. The distance between the center is R. Can you do this?
I will try, sir.
Remember, we are doing the question as magnetic dipole because in most of the notes and most of the sheets that I have, Questions on electric dipole are not there, but questions on magnetic dipole are there. So they are equivalent. Yes or no?
Yes, sir.
Here is your chance to do a question which might appear in your JEE Advanced. I hope you can do this. I'll give you 2 minutes to do this. Let me help you out. Remember the result of this answer. You may not uh, be able to solve this question in an examination hall, but what you got to do is remember the results of this answer, because the result of this answer is very important. Okay. So now this is how you can actually find out, and I hope you can see this. You are taking it as force of interaction between the magnetic field created by a dipole and multiplied by the dipole strength. So you can see here, this is one magnetic pole. The plus pole is the north pole and the negative pole is the south pole. Do we understand this?
Yes, sir.
So if the north pole is here and the south pole is here, north will repel north, but north will attract the south. Yes or no?
Yes, sir.
So there will be one force which is attractive and one force which is repulsive, and that is why these two forces are subtracted. Are you getting my point?
Okay, sir.
Getting my point, beta? And
Yes, sir.
remember, we have put the formula for magnetic field due to a dipole on an axial point, and this is the formula for magnetic field due to a dipole on the axial point. Yes or no?
Sir, by 4 pi m1 square.
It is same as the formula for magnetic electric field due to a dipole. Yes or no?
Yes, sir.
So once you solve this using binomial theorem, you think you have to apply binomial theorem. This is the answer that you will get, and remember, it is a very, very important result that you should remember. Do you see this result?
Yes, sir.
The other way to calculate this is a very, very nice method. And this method, you should remember, this will give you a very important shortcut to remember the force between two dipoles, whether they are two magnetic dipoles or whether they are two electric dipoles. This formula is also valid if you have two current carrying loops and someone asks you what is the force between these two current carrying loops. Are you getting my point, bacha?
Yes, sir.
The only difference would be here we have put M1 and M2. M1 and M2 are the magnetic dipole moments of the bar magnet. In case of two loops, two current carrying loops, this M1 and M2 would be the dipole moments of those current carrying loops. And do you know what is the dipole moment of a current carrying loop?
Yes, sir.
What is that? I into A. I is the current into area vector. That is the dipole moment of a current carrying loop. Yes or no? No, yes.
Yes, sir. Yes, sir.
This formula is also valid, whether you talk about this one or you talk about this one, is also valid for force of interaction between two electric dipoles. The only thing is, instead of mu naught by 4 pi, mu naught is in the numerator, so epsilon naught will come in the denominator. So the answer for electric force between two dipoles, if they are kept like this, will be 1 by 4 pi epsilon naught 6 times m1 m2 divided by r raised to the power 4. Remember, it is inversely proportional to r raised to the power 4. M1 and M2, instead of M1 and M2, you can write P1 and P2, where P1 and P2 are the electric dipole moments of the two dipoles. Are you getting my point? So remember this. Have you noted this down? I don't think you have seen this formula before. Yes or no?
Yes, sir. Yes, sir.
So beta, please note it down. This is the formula when they are put actually like this. Have you drawn the diagram?
Yes, sir.
Actually, and the distance between their centers is r.
R.
There is the second one where one is kept like this and the other one is like this, these are the only two combinations that you will have. So there comes the next one. Here comes the next one. I'll give you 2 minutes to do this. Remember, this is not a question on magnetic dipoles. This is a question between two magnets. This is also a question between a loop kept like this and a loop kept like this. Are you getting my point?
Sir, once explain, sir.
See, when you talk about magnetic dipole moment or electric dipole moment, it doesn't matter whether it is coming from a magnet or from a current carrying coil. You only look for the vectors. You only look for the dipole moment ka vector. Are you getting my point? In the
Yes,
first
sir.
case, how the vector was? Both the vectors, if you look at this, both the vectors, the magnetic dipole moment of this was like this. Are you getting my point, M1?
Yes, sir.
So you look at the vectors, only this vector matters. Now this magnetic dipole moment ka vector M1, whether it is created by a magnetic field, whether it's created by a bar magnet, whether it's created by a horseshoe magnet, whether it's created by a current carrying coil, doesn't matter. The only thing that matters is the magnetic dipole moment is like this. Getting my point?
Yes, sir.
And in the second case, the case which I'm showing to you just now, you can look at that case. What is in that case? Two short magnets, A and B, of magnetic dipole moment M1 and M2 are placed as shown. The axis of A and the equatorial line of B are same. Find the magnetic force on one magnet due to the other. So basically now the scenario is like this, bacha. Basically now the scenario is like this. So what do you see here? One of the magnetic dipole moment is like this. I mean, it's drawn ulta. So let me just put it as south and north. One magnetic dipole moment M1 is like this, and the other magnetic dipole moment is like this. So both the dipole moments are perpendicular. Now I can put a loop. The loop will have dipole moment like this. One of the loop will have dipole moment like this, and one of the loop will be kept like this, which has a dipole moment like this. Both the questions are same. Are you getting my point, bacha?
Yes, sir. Yes, sir. Okay, sir. I'll do.
है ना? Once you have a current carrying dipole, and we will come to that point, when we have a current carrying coil, it behaves as a dipole, right? So you
Yes, sir.
find out the dipole moment M1, you find the dipole moment of the second loop. So this question is the same whether it's put for a loop or for a magnet or for two electric dipoles. So now they are put like this. First case it was put like this. Both were having same direction. Now the answer. What is the answer now? I'll give you 2 minutes. Remember the first answer. You have to also remember the second one. Remember, bacha, this is not more about solving it. This is more about remembering what answer do you get. And you just remember this, that the force in this case is 3 mu naught by 4 pi m1 m2 by r raised to the power 4. Let us not get into how it is achieved. It is achieved in the same way. You can find out magnetic field due to axis between two poles, and then you can calculate it. Okay, getting my point?
Yes, sir.
This bar magnet, you can find out magnetic field along the equatorial line, and then one of this would be getting attracted, the other would be getting repelled, and that is how you can do it. You understand this?
Yes, sir.
You understand this, beta?
Yes, sir.
Remember these two results. I hope you have noted it down. Yes or no?
Yes, sir.
Then comes the next question, and again, do not take it as question of magnetic bar magnet. This is well a question of electric dipole, or this is also a question of two current carrying coils. Getting my point? All are same question. So one magnet is put like this, the other magnet is put like this. One magnet is put like this, other magnet. I mean, yes, I mean, you have to find a magnetic field in between, midway between the dipoles. Can you do that? I'll give you 2 minutes. Well done. I think that is the correct answer. I think that is the correct answer. What you got to do is just remember the formula for one dipole. It is the axial point. For the other dipole, it is the equatorial point, and you just square it and add them. Yes or no?
Yes.
These are the two formulae. This is for the, I think, axial point, and this is for the equatorial point. Yes or no?
Yes, sir.
Add it, square it, and you get the answer. This question is just to make you realize that if a question of this nature comes, you know what is to be done. Yes or no? And then you remember the formula. Then comes the next thing again. Do not take it as question on a bar magnet put in a uniform magnetic field. The same question can come for an electric dipole put in a uniform electric field. The same question can come if you have a current carrying loop placed in a uniform magnetic field. It will experience no force and no torque if the angle is zero. If the angle is not zero, torque will be m cross b. Do we know this? M cross b? Torque on an electric dipole or a magnetic dipole in a magnetic or electric field. Do you know this?
Yes, sir.
So remember this formula. Tau torque is m cross b, whether it's a bar magnet wala magnetic dipole moment or a current carrying coil wala magnetic dipole moment. Just look for the magnetic vector, dipole vector, m vector. If it is for a electric dipole, it is p cross e. Do you know this? Yes or no?
Yes, sir.
Similarly, the energy of a dipole, magnetic dipole, electric dipole placed in a magnetic field or electric field is minus m dot b. You know this? Yes or no?
Yes, sir.
So any question that comes on this is again a question on electric dipole. It could be a question on magnetic dipole. It could be a question on. It could be a question on electric dipole. And then if it is in stable equilibrium, what is the position of stable equilibrium here? When do we say the dipole is in stable equilibrium? When the angle between M and B is how much? 0 degrees. Do you know this? Yes or no?
Yes, sir.
And when the angle is 180 degrees, we call it unstable equilibrium. When magnetic field and dipole moment are in the opposite direction, it is in stable equilibrium. You should rotate it. It will come back to its stable position. Yes or no?
Yes, sir.
In stable equilibrium, when the angle is 0 degree, the potential energy is negative maximum. Yes or no? Minus m into b. When it
Yes,
is
sir.
in stable, unstable equilibrium, it is plus m into b. Yes or no?
Yes, sir.
And if it is in stable equilibrium and you give it a small turn of with a small angle theta, it will oscillate simple harmonically. Yes or no?
Yes, sir.
You must be knowing the value of this omega, mb by I ka root. Yes or no?
Yes, sir.
And if it is electric dipole, it will be eb by I. Yes or no?
Yes, sir.
So you can do a question based on this.
Yes, sir.
And here comes the question. Remember, again I am repeating, do not take it as a question on magnet and magnetic field. This is a question of a current carrying coil like this with a magnetic moment like this. Are you getting my point? Looking at the question. A current carrying coil put like this and a magnetic dipole moment is like this. It is put like this, or electric dipole put like this in electric field. A magnetic field of dipole momentum is released in the uniform magnetic field of induction B from the position shown in the figure. Find its kinetic energy at theta is equal to 90. Its maximum kinetic energy. Will it perform as SHM, oscillation, periodic motion? What is the amplitude? Can you do this?
Yes, sir. I will try, sir.
I'll give you 2 minutes. Remember, this is not a question of magnet in a magnetic field. This is a question of electric dipole in an electric field or a current carrying coil in a magnetic field. Same question, same funda. Okay, then here we go with the solutions. We had to give 3 answers. What is the kinetic energy at 90 degree? We just have to apply law of conservation of energy. Yes or no?
Yes, sir. I got,
Potential
sir.
energy plus kinetic energy at 120 degrees. should be equal to potential energy and kinetic energy at 90 degrees. Yes or no?
Yes, sir.
Then you have to apply where will the kinetic energy will be maximum. Can you tell me at which point the kinetic energy is going to be maximum, bacha?
Sir.
At which point the kinetic energy is going to be maximum, bacha? At which point will the kinetic energy be maximum? Second question was that. Find the maximum kinetic energy. At which point is the kinetic energy maximum? What is your answer? The answer is pretty simple. The kinetic energy is maximum where potential energy is minimum. And where is the potential energy minimum? It is at the mean position. Oh, sorry. Equilibrium position. Stable equilibrium where theta is 0. Do we understand this, beta? That was the point I wanted to make you understand in this question. Get it, beta?
Yes, sir. Yes, sir. Okay.
The first part was very simple. The second part just wanted to find out whether you know at which point is the kinetic energy maximum. Okay. Third part is the motion simple harmonic. Is the motion simple harmonic? The motion is not simple harmonic because theta is very large. Motion becomes simple harmonic only when theta is very small. But it is oscillatory and the amplitude is 120 degrees. So it will start from 120 degrees here, will go to 120 degrees here, and then again this and that. Okay? But it will not be simple harmonic in nature. Do we understand this?
Yes, sir.
Okay. The next question that we are going to do is finding the torque. Finding the torque on the two dipoles. Now, once you find out the torque on the two dipoles, you can also find the energy of the dipole in a magnetic field. So basically, the question here is, you have one dipole like this, and you have other dipole like this. Dipole moment is m2 here, m1 here, and the distance between them is r. You have to find out the torque on one due to 2 and the magnetic energy of this system. Can you do it? Remember, this is not a question just on a bar magnet. This is a question on electric dipole. This is a question on current carrying coils. Do you understand this?
Yes, sir.
Again, remember, it's not about whether you get the answer or not. It's about getting the answer now and remembering it. How do you get the energy? M dot B, M into B into cos theta minus M dot B. You can do that. From there, you can get the energy. Yes or no?
Yes, sir.
To get the torque, just remember it. Torque is M cross B, so you can get it from M cross B. Getting my point?
Yes, sir.
Getting my point? You can find out the magnetic field due to one dipole and cross it. I mean M cross B.
From MB sin theta also you
This
can find out.
dipole and cross with the magnetic field of this dipole. Getting my point?
Yes, sir.
M cross B, that will be your torque. M dot B with a negative sign, that will be your potential energy. Do we understand this?
Okay, okay, sir.
Got this?
Yes, sir.
Or you can do the question in this way. In any way do you do, the answer is what it is written here. And remember all these answers. All these answers of what? Force on the two dipoles. When the dipole were placed like this, when the dipole were placed like this, then the torque when the dipoles are placed like this, and the energy of the two dipoles. Do we understand this? These are the things that you must not forget and note them down. I'll give you 2 minutes to note it down. Then we come to this point. I am not sure whether you have seen this formula. This is the actual Biot-Savart law. Have you seen this?
Point charge.
What do we have here is a charge moving with a velocity v. Now, when the charge was stationary, it creates electrostatic field. Yes or no?
Yes, sir.
When the charge is moving with a uniform velocity, it also creates a magnetic field. Do we understand it now?
Yes, sir.
When the charge is accelerating, then what it does? It creates EM waves. Do we understand this?
Yes, sir. Yes, sir.
Electrostatic field, magnetic field, EM waves. Here, the charge is moving with a uniform velocity. Let us assume that this is a positive charge. It is moving with a velocity v. It creates a magnetic field. And the magnetic field is given by this vector. Have you seen this formula before? V
Yeah.
naught by 4 pi QV cross R by R cube. Everything has to be written with signs. If charge is positive, take it positive. The charge is negative, put it as negative. Do you understand this? Have you seen this formula?
Yes, sir.
Okay, so if you've seen this, that means you don't need to note it down. This is the actual form of the Biot-Savart law. Then you must be knowing the formula for Biot-Savart law due to a straight long wire. Yes or no? This is
Sir.
a standard result that you should remember. You remember this result?
Okay, sir.
You remember this result, beta?
Yes, sir.
Magnetic field to a straight wire. You have this angle
Yeah,
as
yeah.
theta 2 and this angle as theta 1. And this is the formula. And you find out the magnetic field using the right hand thumb rule. This is the
Yeah,
current.
yeah.
This is the
Yes, sir.
point.
Yes,
The
sir.
magnetic field would be inside. Remember this?
Yes, sir.
Okay. Then again, you can see a variation of this simple problem where you have a wire like this and you find out the field at this point. You can just calculate it. Yes or no? This would be the magnetic field. You know this?
Yeah. Yes, sir.
Okay. So I don't have to waste my time here. Okay. Okay. Then can you tell me the answer to this one? A simple one. This is a wire which is coming from infinity. Then again, this is going to infinity. And then there is a square loop in between. What is the magnetic field at the center O? I'll give you 2 minutes to think about it. I think you got stuck here. The answer is 0. Why is the answer 0? This wire will not create any magnetic field because the point is straight ahead. Yes or no?
Yes, sir.
This wire will not create any magnetic field because the point is backwards straight ahead. Yes or no?
Yeah.
Now,
Yes.
remember, whenever you get a question of this type where current is getting divided, wherever you have more resistance, here both the resistance are same. If this question could have been put in a different way, and I'll just try to put it up. Wherever there is more resistance, current would be less. Yes or no?
Sir,
Where
it
there
is
is less resistance, current would be more. Here, both the cases are same. Here, whatever current goes in this part, the same current will go in this part. Yes or no?
Yes, sir.
So whatever magnetic field right part is creating, left part will cancel it out. Yes or no? So the answer would be
0.
0. Now, I could make a case where current is not getting equally divided, and let me take you to that case. And how I'll take you to that case, I will bring my sheet on and try to make a sense here. I hope you see my sheet now, right?
Yes.
Now see, I could make a example where, okay, let me not make it this way. I have a better way of doing it, and the shape. Okay, I have this, and it is round or not? Okay, it looks round. I have a current coming from here, from infinity, and let me just put it like this. Current coming from infinity here, and then it is going to infinity from here. This is point A, this is point B. So how is the current going to get divided, bacha? Some current will go in this branch and the other current will go in this
Downwards.
branch. Yes or no?
Yes, sir.
This is O and the radius of this is R. Now if I frame the same question, bacha, If I frame the same question, what is the magnetic field at point O? What is the magnetic field at point O? This circle is better. What is the magnetic field at point O in this case? If I call the current as I, what is the magnetic field at point O? Now, you saw in the previous case where it was a square, you could easily see that the current was getting divided in half, and the right hand side or the left or the downside will cancel the upside. Does the same thing happen here?
No, sir.
So,
Again,
so the
sir.
answer in this case will not be 0. Yes or no?
Yes, sir.
No, the answer will still be 0. The answer in this case will be 0. Why so? If I call this current as I1 and if I call this current as I2 beta, current will divide in inverse ratio of resistances. Do you know this?
Yes, sir.
Now here I1 wala part ka resistance is less, so I1 will be more than I2. Yes or no?
Yes, sir.
But
Okay, sir,
I1
sir.
wala part is less. So if I apply the formula for electric current due to a loop, this is only pi by 2. So the length of the loop is less. Yes or no?
Yes, sir.
But here the current is less, but the length of the loop is more. Yes or no? The length of this loop is 3 pi by 4, 3 pi by 2. The length of this loop is pi by 2. The resistance is also depend on the length. Pi by 2 wala length has 3 times less resistance than 3 pi by 2 wala length. Yes or no?
Yes, sir.
That means what? Whatever magnetic field pi by 2 wala part will create, the same magnetic field but in the opposite direction will be created by 3 pi by 2 part. Yes or no? And they will cancel each other out. Do we understand this? If I call the resistance of this part as R, the resistance of this part would be 3R. Yes or
Yeah.
no?
Yes, sir.
So I1 current will be 3 times more than I2 current. Yes or no?
Yes, sir.
But the length of the part, the angle of I1 is pi by 2 and angle of I2 is 3 pi by 2. So again the 3 factor will come and they will cancel each other out. Yes or no?
Yes, sir.
That means wherever a question of this type comes where the current is getting divided, it will divide in inverse ratio of resistance, but again it will cancel out. So the net answer in all these cases would come as 0. Do we understand it now?
Yes, sir.
No doubts on this one?
Yes, sir.
Can I give the next question?
Okay, sir.
I think you would have done a question of this nature, but let me try this. Give me the answer for this one, fatafat. A similar question has come in a JEE where they asked the force on a wire which was kept along the y-axis. You understand the field, the force is simple. In the figure shown, two wires W1 and W2 are each carrying current I are placed parallel to each other along z-axis. The direction of current in W1 is outward, which is shown by the dot. The direction of current in I2 or W2 is cross, which is inside. Find the magnetic field at point P and Q. P is perpendicular bisector at a distance root 3a. Q is not the perpendicular bisector. I'll give you 2 minutes to do it. If you're finding difficult to find out the direction of magnetic field, it's very simple. See, it's dl cross r. Yes or no?
Sir?
How did you get a magnetic field? It is mu naught I dl cross. What is the formula for magnetic field due to a small segment of a wire?
P into 2.
Do you remember that formula, beta? Small wire. What is the magnetic field due to a small wire? How do you get it? I just
charges and Q.
bypassed that part because I thought that you know it. DL cross R or R cross DL. What did we do? Well, DL cross R, na?
R cross
R
DA,
cross
sir.
DL.
R cross DA.
R cross DL or DL cross R? Got confused? It was DL cross R. Yes or no?
Maybe sir, not getting.
You want me to show it?
Yes, sir.
Okay. So let me take you back there. Don't worry. I will just brush back, brush back, brush back. And this is what you got to remember. It is DL cross R. Okay. It is what? DL cross R. Remember this current carrying element cross R?
Okay. Sir.
So magnetic field is DL cross R, bacha. It has to be perpendicular to both the current carrying element and your R vector. Do you understand this? And that
Sir.
is why you find out the direction of magnetic field using the right hand thumb rule. You put your thumb in the direction of DL and you put your palm in the direction of R. Yes or no?
Yes, sir.
Now, coming back to the question that we were discussing, or any question, remember, magnetic field is always in a closed loop. Do you know this? So it is.
Yes, sir.
So, in case of an infinite wire, this magnetic field is actually moving in a closed circle. Do you know this?
No, sir.
That's it. Now let us come back to the question. Now, the center of this circle is at this point. Which point? The point where you have put the wire. Yes or no? This is the point where the center of the circle is, right? And this is coming out. So DL is coming out. R is like this. And I'm going to draw this R on the sheet. Do you see this R? DL
Yes, sir.
cross R.
Yes, sir.
It has to go perpendicular to this direction, bacha. Getting my point? In fact, if I draw it, it is moving in circle like this. My circle may not be perfect, but it serves the purpose. Are you getting my point?
Yeah, yes, sir.
Now look at the magnetic field created by this inward wire. DL is here. And I make it like this. DL cross R goes like this. In fact, if I make the circle and I might not be able to make a perfect circle, the magnetic field will go like this. If I find it at this point, it will go like this. If I find it at this point, it will go like this. If I find it at this point, it will always go tangential. Are you getting my point, bacha? My
Yes,
diagram
sir.
may not be very good because it's difficult to draw a circle here. Getting my point, bacha?
Yes, sir.
Now
Sir,
you should be able
mu
to
naught
solve
I by
the
4
question.
pi
Yes
A.
or no?
Yes, sir.
Okay. So now, as you can see here, bacha, as you can see here, both the magnitude would be same. One of the field, the blue field is going like this. Are you getting me? Getting my point, bacha? And the red field is going here. Yes or no?
Yes, sir.
So their vertical components will get added up and the horizontal components will get cancelled out. Yes or no?
Yes, sir.
You can calculate it from here. Yes or no? Up till here only. You can calculate it. Yes or no?
Yes, sir.
Pakka?
Yes, sir.
Now can you solve the second part? What was the second part? In second part, you have to find out the magnetic field at the point Q, and let me just take my fancy drawing away. It's not creating a big impact. Let me take it here. This is out. This is out. Can you find the magnetic field at the point
Q.
Can you do it?
Yes,
Remember,
sir.
this Q point
Mu
is
naught I by 4 pi
directly,
A root of 2 minus 1.
this Q point is directly above this point. Okay, do you understand this?
Yes, sir.
So now the magnetic field to this will be, this is going down, this is going here. So this red magnetic field will go like this. Are you getting my point, bacha?
Oh. Oh.
you just understand the direction, beta, everything becomes simple. And the blue magnetic field,
Yes, sir.
up, ding, ding. So the blue magnetic field will go like this. Are you getting my point, bacha?
Yes, sir.
Now you can break it into horizontal and vertical components, and you should be able to get the answer.
Yes,
Similar
sir.
question
Got it, sir.
has come in JEE, and this is the answer for that question. I hope you understand this. This
Yes, sir.
gentleman,
Same.
my dear friends, is your blue field, and this gentleman is your red field. Yes or no? No, yes.
Yes, sir.
Shall we move on to the next question?
Next month, sir, I will note
And
it.
remember, this might be a question, but you will have to remember this. This is the magnetic field due to a sheet of width y. You must remember this is a standard result. I hope you know the answer for this one. Yes or no?
Yes, sir.
What is the answer for this one?
I will do it, sir. I know this.
Remember all these short answers, beta, because I don't want you guys to waste any time in solving these questions. And the standard answer is this: mu naught
Sir, mu naught I by 2 pi ln A plus W by
W कहाँ
A.
गया? Mu naught I by 2 pi W, beta.
Ah, yes, sir.
Remember these standard results. Yes or no?
Yes, sir.
You must be knowing magnetic field due to a circular loop, a
Yes,
part
sir.
of the loop. Yes or no?
Yes, sir.
You must be knowing magnetic field due to a circular coil. Yes or no on the axis?
Yeah, yes, sir. Yeah.
Okay. I hope you remember these questions, these formulae.
Yes, sir.
Okay. These are simple questions. I hope you can do this. Yes or no?
Yes, sir.
There's no point wasting your time here. Now comes this one, and I would request you to remember this standard result. This is the magnetic field on the axis of a solenoid. Have you seen this result? V naught Ni by 2. Have you seen this result?
As
Yes or
question we
no?
have
No, yes.
solved like this.
नहीं देखा?
Sir?
Have you seen this result before? No?
As question we have solved this, sir.
So you remember this result like this. This is, what do you see? This is a solenoid, yes or no?
Yes, sir.
I is the current in the coil of the solenoid, yes or no?
Yes, sir.
What is N?
Number of turns.
No, number of turns per unit length. Do you understand this?
Got it.
And
Yes,
you
sir.
remember this formula like this. Instead of remembering this angle as theta 2 and this angle as theta 1, which confuses me, you will draw a perpendicular line. You will call this angle as theta 1 and you will call this angle as theta 2. Instead of cos theta 1 minus cos theta 2, your answer will be sine theta 1
Yes, sir.
plus
Plus
sine
sine theta
theta
2.
2. So this question looks exactly similar to the magnetic field due to a wire.
Solenoid, sir.
Instead of mu naught I by 4 pi r, you are getting mu naught Ni by 2. Will you remember this now?
Yeah.
Okay.
Yes, sir.
So remember this result in this way, because I think this is easier to remember this way. Then for an ideal solenoid, ideal solenoid means a solenoid whose length is infinite. The answer becomes mu naught Ni. Yes or no?
Yes, sir.
Because both the angles become 90 degrees each.
Yes, sir.
Okay, so you remember this, so there is no point on wasting any time on this. Do you
At one
remember?
end, mu naught Ni by 2.
If it is a semi-infinite, it becomes mu naught Ni by 2. Okay,
Yeah.
you got this?
Yes, sir.
Okay, then let me just give you a question. When I was looking at one question and just want you to do it just for my satisfaction, so that I understand that you've understood. Where is that question? Okay, that question is here in this sheet. Again, this is a question taken from Irodov, a very old book, not very popular these days, but it was popular in my time. So most of these questions that you see of loops are taken from Irodov only, and this is a very simple one. This is an infinite wire coming from the x-axis. They have drawn the x-axis. Then it comes on the page, then it turns, and then it again goes to infinity. You have to find the magnetic induction or magnetic field at point C. Can you do this?
All right, sir.
Point C is the center. I'll give you 2 minutes. Let us look at how we are going to solve it. And remember, there are magnetic field going in different dimensions. Do you understand this?
Yes, sir.
So the magnetic field due to the circular loop is going along minus x-axis inside. Yes or no?
Yes, sir.
And the magnetic field due to the two wires is going along minus the axis. Yes or no?
Yes, sir.
So this is the answer, and I don't think you gave me the correct answer.
Yes, sir. Just the mistake.
What was wrong? You were not able to find out the direction of magnetic field.
Direction भूल गया, sir.
What was wrong? Y which is coming out, it is going to create magnetic field in the downward direction. Yes or no?
Yes, sir.
Y which is
It's,
going
just-
in will also create field in the downward direction. Yes or no?
Yeah.
Y which is on the plane of the board
It is in the inside of the
it will
direction.
create field in the inward direction. Yes or no? Inside direction is minus x. Yes or no?
Yeah, yes, sir.
So don't make a mistake in finding out the direction. I hope you understand this.
Yeah.
Okay. Then I hope you have gone through Ampere circuital law.
Yes, sir.
Yes or no?
Yes, sir.
Okay. You know its various applications as well. Yes or no?
Yes, sir.
Okay. So remember these standard results and we calculate these results using the Ampere circuital law. If you have a hollow current carrying infinitely long cylinder, inside the cylinder there is no current. Yes or no? If you make a loop, you will have no current. So inside the magnetic field is always going to come how much? 0. Yes or no?
Yes, sir.
And if you go to any point outside at a distance r, what will be the magnetic field? This will be the magnetic field exactly
Yes, sir.
same as the
By
magnetic
2
field
pi.
due to an infinite wire. Yes or no?
Yeah, yes, sir.
Okay, remember this. If it is a hollow cylinder, and remember this graph, bacha, these graphs are very important because sometimes instead of asking you the question directly, they might just give you the graph. And I hope you can see this graph. Can see this graph, bacha?
Yes.
Inside the magnetic field is 0. On the circumference, it is highest, and then it is goes down. Yes or no? We get this?
Yes, sir.
Yes or no, bacha?
Yes.
You know this graph? You see this graph now?
Yeah, yes, sir.
If you have a solid cylinder will have current density. Then what are your answers? Current density is total current I divided by pi r square. What are your answers now? Do you know their standard results?
Yes, sir. Just one, sir. I'll calculate.
Yes. So remember this standard result for inside, and remember the vector form as well, because this vector form will help you in getting questions which
mu naught by 2 J bar plus R bar.
mu naught J cross R by 2. This is
Yes.
for R smaller than capital R. Yes or no?
Yes, sir.
Then we have magnetic field outside,
R
and
is
the
greater than
formula
R.
may look somewhat exaggerated, but this is how the formula looks like. Again, remember J cross R. Yes or no?
Yes, sir.
And this is the diagram. This is the graph. You know this graph. Yes or no?
Yeah, yeah.
Okay. So you know this. Then you have this question. Now this question is similar to the question that you have done in electrostatics. Instead of a sheet which carries charge, this is a sheet which carries current. And sometimes the current is given as lambda. The current per unit length is given as lambda. Here current per unit length is given as k. That means that if you take a length dl on this infinite long sheet, you understand infinite long sheet?
Yes, sir.
If you take a small element of length dl, the current will be k into dl. So k or lambda becomes your current per unit length.
Yes, sir.
Do you know
By
the standard
applying
result for
amperes.
this?
By applying amperes law, will do, sir.
Yes?
Yes, sir. By applying amperes law.
Yeah, so do you
Yes,
remember
sir.
the standard result? It is
Yes, sir. Mu naught I by.
mu naught lambda by 2. Yes or no?
Ah,
Now this result is exactly similar to the electric field due to an infinite sheet. Sigma by 2 epsilon naught. Yes or no?
yes, sir.
It was sigma by 2 epsilon naught. Remember epsilon naught in the denominator means mu naught in the numerator. Here it was charge per unit area. Here it is current per unit length. So remember these results. I hope you will be able to remember these results. Yes or no?
Yeah, yeah, yeah. Yes, sir.
Okay. So if these questions are done, solid cylinder is done. Hollow cylinder, point on the hollow cylinder, sheet. Okay. Magnetic field due to a solenoid is done. Done. This question is done. This is done. Then we move on to questions on magnetic force. Are you ready for questions on magnetic force?
Yes. Huh?
Well, I will let me see if I have. Just give me a minute. Let me just see if I have questions on. Hmm. Okay. Let us solve this question. A long carrying wire, and I don't know. Maybe this question comes in the GE. A long current carrying wire I is bent into form of plane angle theta. Do you see this question? Find the magnetic field B at a point B on the bisector at a distance x is written in the form of K cot theta by 4. Find the value of K. I'll give you 2 minutes to do this. Well, the answer is K is mu naught I by 2 pi x. Beta 2 was dimensionally wrong, right? You have to solve. So
Nice,
see,
sir.
you have drawn the diagram like this. This is one current carrying wire. This is the other current carrying
Sir, I
wire.
got same. First I told that one, no, sir. Yes, sir. I got same, sir.
You got same, but you got confused.
ये सब बोलने का नहीं है इसलिए नहीं बोला.
See, beta, you'll have to get me the correct answers. If you know this and still you do a mistake, it cannot be pardoned. Yes or no?
Yes, sir.
You did the same thing,
Almost.
bacha?
Yes, sir. Almost I did, sir. It's came.
Okay.
But
You realize your mistake.
uh, you not
Okay. Chalo, then I'll have to do one more problem because I was just moving ahead, but now I got stuck. Chalo. These are the problems. These are the type of problems which you will find in a JEE. Four infinitely long L-shaped wires, each carrying current I, have been arranged as shown in the figure. Obtain the magnetic field strength at point O, equidistant from all the four corners. Interesting, no? 2 minutes. And the answer, my dear friend, is 0.
0.
0. How come 0?
Nice, sir.
नहीं sir.
8.
Possible नहीं sir. Not possible, no. Do we understand that all the magnetic field due to all the wires would be same? Yes or no?
Yes, sir.
We just have to see whether the directions are coming same or not.
Yes, sir. Same era.
You just have to see, and that is where you get caught. Yes or no?
0.
See, look at the vertical wires. Look
Yes,
at
sir,
the
they are in
vertical
same
wires.
direction.
The vertical wires on the left hand side will create field outwards. Yes or no?
Yes, sir. Outwards.
But the vertical wires on the right hand side will create field
Inward.
cancels. All are same.
Oh, yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yes sir. Yes sir. Yes sir. Then horizontal wires on the top will create field outwards.
डायरेक्शन से नहीं दिखा सर मैंने किया.
अरे यार sir, it doesn't happen that way, na sir. You have to see the direction, sir. So the answer is
0.
yes, yes, yes. Now it is clear. It is 0. Yes or no?
Yes, sir.
Now you can clearly see that it is 0, right? You should have seen that before.
नहीं सर मैंने. It's my mistake. Okay, sir. Next time it won't be.
Okay. Now you have one more chance to redeem yourself. Do you
What,
want to
sir?
redeem yourself?
Sir?
Redeem means, get your status back. This one. Get the answer for this one correct. Then I'll give you your due.
रुको सर मैं ट्राई करूंगा.
Okay. I'll give you time. See, the hint was there. There was no distance given anywhere, right?
Yes,
So
sir.
the obvious answer would be 0. But why it is 0? Why it is 0, bacha? Because there is no current in the circuit. This was more a question of what? It was more a question of electric circuit rather than a question of magnetic field. Are you getting my point, bacha?
Yes, sir.
If you could have applied your favorite nodal theorem, you could have found out that there is no current in the loop. Yes or no?
Yes, sir.
No branch gets any current. If there is no current, there is no magnetic field. Yes or no?
Yes, sir.
See, sir, it was simple, sir. Na? Yes or no, sir?
Yes, sir.
Okay. So remember this. Then again, just one question again. These 3 questions are taken from that Irodov, and you can just understand. I think we have done one of these 3 questions, and if not others. In the next class, we'll be doing more tough questions. First, we will do simple questions on magnetic force, and then we will move on to the tougher ones. Okay? So that is how we will move. Got it? These
Yes,
3
sir.
questions again taken from Erodo, cut, copied, and paste. I hope you can do this. We have done this question, right?
Yes, sir.
We have done question number 1. In question number 2, this wire instead of here, it goes here. So you understand this, how it is to be done? In question number 1, this y is coming from minus x. I mean, this is going along minus x and this is going along plus x.
Plus x.
And this lies in the zy plane. Yes or no?
Yes, sir.
In this question, this wire is going along minus x. This wire is going along minus y, and this is in the yz plane. Yes or no?
Yes, sir.
In the third question,
Both are in.
this is going along minus x. This is coming from plus x, but again the direction has changed. Okay.
Change it to minus x.
So you will be able to do this. Yes or no?
Yes, sir.
Okay. So these 3 questions again taken from Herodo. So you can do this. The next class we will be doing more tough questions on the same topic, and we will try to wind up magnetic field and magnetic force probably by the next class, and then we'll move on to maybe EMI in the next class. Okay.
Sir.
So I'll see you in the next class tomorrow, and I
sir.
hope you enjoyed this class. So I'll see you tomorrow. Take care.
Yeah.
Have a nice day, beta. Bye bye.